Welcome back. Now we're going to look at section 1.3 out of the book, which is vector equations. A couple of definitions. A row vector is a matrix with one row. We've already seen that a matrix is just a square grid of numbers. So a row vector is a matrix with just one row, and a column vector is a matrix with one column. And when we say vector, if we use just the term vector in this course, we're going to mean a column vector. Now, when we talk about a vector, we usually give it a lowercase designation. So a lowercase u or lowercase v. When we talk about an individual number, we also give it lower cases. So scalars, we give it lowercase numbers. When we use an uppercase letter, we're usually talking about a matrix. So lowercase letters refer to an individual element, a number, or a vector. So just a couple of examples. U equals that's a column vector or a vector. If we talk about U2, when U is a vector, U2 is the second element of the vector, so the -1. So the ith entry in the vector. If we have a row vector, which we will use a little bit in this course, but not as nearly as much as column vectors, we can also denote it by a lowercase letter, and the same thing, V3 is the third element in that row vector. Vector addition, pretty straightforward. The only thing to remember is you have to have the two vectors being the exact same size. You are not allowed to add vectors that are different sizes. So the sum is just obtained by adding the corresponding entries of u and v. So as an example, the vector 3, 4 plus the vector 1, -1 is 4, 3. A scalar. Well, we'll talk about scalar in this course. A scalar is just a real number. Okay. A scalar multiple of a vector is the vector obtained by multiplying every entry in the vector by the same constant. So a couple of examples. 2 times the vector 3, 4 is 6, 8. -3 times the vector -2, b minus 2c, gives this vector. Again, you just multiply every element in the vector by the number. That's scalar multiplication. When we're talking about R2, well, there's one thing I didn't mention. If we're talking about all vectors with a certain number of elements, so all vectors with 2 elements is described as R2. All the vectors with 5 elements is R5, and so on like that. So that's just a shorthand notation of saying all of the vectors of this size. Okay. So when we're dealing with R2, vectors with 2 elements, we have a geometric interpretation of them. So a vector in R2, such as the vector 3, 1, you can represent it as a geometric point on the plane. So it's the point 3 in the horizontal direction and 1 in the vertical direction. That gives us the point 3, 1. So you can think of it as the point 3, 1. Or you can also think of it as a vector, the line, the arrow that starts from the origin and goes to that point. So a couple of different ways of thinking about it on the plane, depending on the circumstance. Vector addition can also be represented on the plane using the parallelogram law. So when you're adding 2 vectors, you form a parallelogram with the adjacent sides representing those vectors. So as an example, we can sketch the vectors 2, 3, and 4, 1. So first the vector 2, 3. So 2, 3 would go up to about here. And this time we're going to use the arrow. 4, 1 would go to about here. The parallelogram law says, well, this gives you 2 sides of your parallelogram. Use that again to make the other 2 sides. So that makes a parallelogram. And then your sum is the vector from the origin to that point you've just created. So this was 4, 1. This was 2, 3. And after you build this parallelogram, you have that this is going to be the point 6, 4. Okay. So vector addition has this correspondence on the plane to parallelograms. Now, when we talk about adding vectors, there are a number of properties of them. These are called algebraic properties. So things to know about adding them. Now, these things may seem obvious. When you're used to adding just numbers, you're going to see that this is very much the same as when you're just adding numbers, or when you're dealing with algebra and you're dealing with variables for scalars. When we get to matrix multiplication, we're going to see that there are some differences. But for now, this should look very similar to what you're used to when you're dealing with numbers and equations where variables represent scalar numbers. So the first thing is u plus v equals v plus u. That's called the commutative law. It says if you're adding two vectors, it doesn't matter what order you add them in. You can flip them back and forth. You're going to get the same thing. Second one is the associative law. It says if you're adding three vectors together, it doesn't matter if you add the first two and then add the third one, or if you add the second and third one and then add the first one. So these two laws together mean that when you're adding a whole bunch of vectors, you can rearrange them, you can add them in whatever order makes it most convenient. Okay? Again, I'm going to caution you, when we get to matrix multiplication, that is not going to work. It's going to be different. But for now, when you're dealing with addition, it's the addition that you're used to. The third one, adding the zero vector to a vector just gives us that vector back again. Now the 0 in here is the vector in our n. So n elements, that's all zeros. So it's 0, 0, 0, however many you need. Fourth one, u plus negative u equals 0. Now, technically, what does negative u mean? This is u plus the scalar negative 1 times u equals 0. So it's just a shorthand for saying scalar multiplication of negative 1 times u. Add that to u, you get 0. Again, exactly what you're used to from normal numbers. It also works with vectors. The fifth one, that's dealing with when you start combining vectors and scalars. So a scalar times u plus v is equal to su plus sv. So in other words, you can add your vectors together first and then multiply, or you can multiply each of the vectors first and then add them. You get the same thing. The next one is s plus t times u equals su plus tu. If you have two scalars and a vector, you can add your scalars first, then multiply, or you can multiply first and then add. These two combined are called distributive laws. G, the seventh one. Scalar multiplication, where you have two scalars. You can multiply the scalars first and then multiply the vector. Or you can multiply one of them by the vector and then multiply the other one. Now, one thing to keep in mind here when you're dealing with multiplication of vectors, normally you write it as the scalar times the vector, like that. So in other words, you'll get something like 5 times the vector 3, 2 equals 15, 10. You normally put the scalar on the left-hand side. You don't typically put the scalar on the right-hand side. There's just a convention, and there is actually a reason for this, but we'll see that later. And finally, the vector, the number 1 times a vector gives you the vector back again. That's the scalar 1. So these are the algebraic properties of vector addition and scalar multiplication. These are the things that let you combine and shift around things to make it more convenient to create linear combinations. What is a linear combination? Well, this whole course is going to deal with linear combinations of vectors. A linear combination of vectors, where you have n vectors, is the sum of this form where those c's are scalars. So it's a number times a vector, plus a number times a vector, plus a number times a vector, plus a number times a vector, and so on until you've used up all your vectors and your scalars. That's called a linear combination. So as an example, if you have these two vectors, u and v, then 3u minus 2v is a linear combination. It's a number times a vector plus a number times a vector. So 3 times u plus negative 2 times v. That's a linear combination. You solve for that, and you should get minus 2, 7. Okay? Give it a try just to make sure you know how to do that. One of the big questions we're going to be answering in this class is saying, is something a linear combination of something else? So in other words, is 1, 3 a linear combination of those two vectors? This is saying, can I combine those two vectors, something times 1, 1 plus something times 2, 3, and end up with 1, 3? And the answer is yes, I can. And I give you the answer here. Negative 3 times the first vector plus 2 times the second vector gives us 1, 3. So 1, 3 is a linear combination of those vectors. I can get that 1, 3 by a linear combination of the vectors I start with. That's one of the big questions that we're going to be solving over and over in this class. Is something a linear combination of something else? So, for example, let's work through a problem. If we have u and v equal to those two vectors, determine if w equal to that is a linear combination of u and v. So in other words, is it a linear combination? So we're asking is x1 times 1, 2, 3 plus x2 times v, 4 minus 1, 2, is that equal to minus 2, 5, and 4 for some x1 and x2? That's what it means. Is something a linear combination of something else? So written in vector form is x1u plus x2 times v equal to w for some x1, x2. That's what we have to try to determine. So if we take that equation, we can rewrite it. Let's take the x1 and put it inside, because remember, this is a scalar multiple. This x1, that's a scalar times a vector. A scalar multiplication is you just take the scalar times everything inside. So this is asking, this is the equivalent of saying, is x1, 2x1, 3x1 plus 4x2, negative x2, 2x2 equal to negative 2, 5, 4. Okay, that's just taking the scalar and putting it inside the vector. Or, well, now we can add these vectors. x1 plus 4x2, 2x1 plus, that one's a minus, minus x2, 3x1 plus 2x2. We're asking, is that equal to negative 2, 5, and 4 for some x1 and x2. Or we can rewrite it again as x1 plus 4x2 equals -2. 2x1 minus x2 equals 5. 3x1 plus 2x2 equals 4 for some x1 and x2. This is a system of linear equations that we've already seen. And we have seen that we can solve these by using the augmented matrix and our Gauss-Jordan method. So this is 1, 2, 3, 4, -1, 2, -2, 5, 4. That is our augmented matrix. Now we apply Gauss-Jordan elimination on it, or the Gauss-Jordan method on it, and we see if we can get a solution. Is there a solution to this? Well, let's see. Our matrix is 1, 2, 3, 4, -1, 2, -2, 5, 4. Start to eliminate it. So our first leading entry, we are going to take 2 row 1 minus row 2 is the new row 2. That gives us row 1 stays the same. Our new row 2 becomes 0, 9, -9. And our row 3 stays the same. Now we're going to get rid of the other number below our pivot element, or our first leading element. So we're going to take 3 row 1 minus row 3 is the new row 3. That gives us 1, 4, -2, 0, 9, -9, 0, 10, and -10. Now, I'm going to start to simplify this a little bit. The Gauss-Jordan method technically says identify your next leading element and solve for everything underneath it. I'm going to do it a little bit differently just to make it easier. I am going to recognize now that if I take 1/9 row 2 becomes my new row 2, I'm going to make my life a little bit easier. 1, 4, -2. This becomes 0, 1, -1, 0, 10, -10. Now I can take 10 times row 2 minus row 3 is my new row 3. I get 1, 4, -2, 0, 1, -1, 0, 0, 0, all zeros. Again, I'm trying to get all the zeros on the bottom if there's any rows of zeros. So now I have my leading entries. Gauss-Jordan method says get rid of the numbers above your leading entries. So now I'm going to do row 1 minus 4 row 2 is my new row 1. Gives me 1, 0, 2, 0, 1, -1, 0, 0, 0. Now I'm in row reduced echelon form, and I can read off my solutions. My solution is x1 equals 2 and x2 equals -1. It is a unique solution. So this means that the vector I started with, -2, 5, 4, is a linear combination of my two vectors, 1, 2, 3, and 4, -1, 2. I can combine those two vectors to get the W vector, the -2, 5, 4. So it is a linear combination. So an observation out of this. A vector equation, so a vector equation is a linear combination where the u's here are vectors, and the b is a vector, So a linear combination, or a vector equation, is a linear combination of vectors equals a vector where all the vectors are the same size. That's called a vector equation. That, if it has the same solution set as the linear system, so the linear system of equations, whose augmented matrix is that. So take your vectors out, put them as the rows in your matrix, take your constant matrix, constant vector, put that as the final one, build your augmented matrix, solve for that using Gauss-Jordan method, and it has the same solution set as your vector equation. In particular, we say that B, your final vector, can be generated by a linear combination of those U's if and only if there's a solution to this linear combination using your augmented matrix. So, linear combination, vector equations, solutions to vector equations is the same task as solutions to systems of linear equations. They're just two different ways of writing down the same problem. Okay, so we've had a couple of questions here saying, is something a linear combination of other vectors? Quite often what we do is we turn this on its head and we say, here's a set of here's a set of vectors. Describe all of the possible linear combinations of those vectors. That is called a span. So the span is the set of vectors that is all possible linear combinations of those vectors. And we denote this as the span of those vectors. And this is turning it around. It's not saying, is something a linear combination of other things? It's saying, describe all of the possible linear combinations of something. And we're going to be using this span throughout the course. Okay, that's it for today, for this lesson. That's a fairly short one. Next one is going to be dealing with the next section of the book.